Okay, so let's talk about when two vectors are orthogonal. So if I've got a set of vectors, u1 all the way up through up, so a set of p vectors in Rn, they are orthogonal if each pair of distinct vectors from the set is orthogonal. So no matter which two I pick and I do the dot product with each other, right? Not itself, but with each other, that every single one of them is the dot product is 0. So so what that gives us is if I have this set of p vectors that are an orthogonal set, then that set is linearly independent and is a basis for some subspace spanned by S. So not see there's p vectors in Rn, so it doesn't necessarily span all of Rn, but wherever this S spans, as long as this set, if they are orthogonal, they will make a basis. So if it's orthogonal, then it will be independent and it will span that S. Okay, so the orthogonal is huge. It gives us a lot of things. So here's a little bit of a proof. So let's just say I have 0 is a linear combination. Oh, that should not be capitalized, right? That's a constant C. So 0 can be written as numbers times this vector, all these vectors in the set. So if I take this 0 and I dot, so I rewrite this 0 here, it is the same thing as, what did I do here? I'm sorry, hold on, let's say, oh, no. I took each side here, this side and this side, the left and the right side, and I dotted it with U1. So I dotted it with U1, dotted it with U1. So this is 0 dotted with U1, and because this is the 0 vector, this gives me 0. And so I'm dotting this right-hand side with U1. So what does that look like? So U1 times this, U1 times this next vector, U1 times this vector, right? So here's C1, the number C1, U1 times U1, right? Sorry, U1 dot U1, and all the way along this CP, UP dot U1. Okay, so I've been told that this is an orthogonal set. So what do I know about all of these in between, all like UP times U1? All of these will give me 0 because U1 is orthogonal to every single one of the other guys. So what I end up getting is all of these other guys here are 0, and I end up getting this statement here. And so U1 is non-zero, right? Because it's an orthogonal set of non-zero vectors. U1 is not the 0 vector. So that means that U1 dot U1 is not 0. So the C1 is 0. So what that means is that all, and so this means this C1 is 0. So I can go through this whole set, this whole proof again, and dot both sides with U2, U3, all the way up through UP, and find out that the only way I get to 0 is with all the constants equaling 0. So that means they're linearly independent. A little bit of a proof there. You don't need to know that. Just thought I would just show it to you. Okay, so an orthogonal basis is a basis that's linearly independent and spans, right? A basis is a linearly independent set that spans. And so if it's that is also orthogonal. Orthogonal basis is orthogonal and a basis that's independent and spans. Okay. So let's show that these two vectors form an orthogonal basis. So first dot thing I'm going to show is that their dot product is 0, because that shows that they're orthogonal. So I get 12 minus 12 equals 0, check. That's means it's orthogonal. Okay, so what else do I need? A linearly independent set that spans. So I'm going to put these two vectors into, and it spans R2, right? Into a matrix, and I'm going to do the row echelon thing on my calculator. I get this. So I see a pivot every row. That means it spans R2. Pivot every column. That means it's linearly independent. So that means I have an orthogonal basis, right? If it spans and is linearly independent, I have a basis. So that means I have an orthogonal basis. All right. So let's look at what we have here. So if I have this set that's an orthogonal basis of for some subspace W of Rn, not all of Rn necessarily, so it's only P vectors. So if I have some subspace W that has this as a basis, now what I'm going to do is I'm going to show you a different way to find the constants in front of the basis vectors using the dot product. So let me just give you a bit of a proof here. So if I take this line here, right, the left-hand side and the right-hand side, and again, I'm doing that same kind of nifty thing as I'm dotting both sides by U1. This is just in proof land, right? Dotting both sides by U1 on the right-hand side. So then this y dot U1 gives me C1 U1 dot U1. So let me just write that over here. Y dot U1, and these are both vectors, is equal to C1 times U1 dot U1. Okay, so what I want to do is I want to solve for this C1. I want to find out what this constant is. So solving for that C, I have Y dot U1 in the numerator, right there, and then U1 dot U1 in the denominator. So that's what my constant is. So just taking this true fact and multiplying or dotting both sides by U1, I get this. So this pattern here is one you need to memorize. So what we're going to say is Y is going to equal to C1 times U1 plus C2 times U2. And so C1 is Y dot U, I'm sorry, I should put a U1 and U1 there. Y dot U1 over U1 dot U1. And that's all times U1. I'm just going to write what the U1 vector is, right? So Y dot U1 over U1 dot U1, all times the U1, plus Y dot U2 over U2 dot U2, all times the vector U2, which is 6, 4. Now let's go do it. So Y dot U1, so the vector Y is 9, negative 7, so I'm transposing that, times U1, 2, negative 3, U1, which is 2, negative 3, 2, negative 3. So all of this will be a number. Then I'm going to multiply by U1, plus. So let's do the same thing. I'm just going to set them up. U2, which is 6, 4, and then down here, 6, 4, dotted with 6, 4, and that's all going to be times 6, 4. Okay, so the vector Y, so let's do the multiplication here. So I get 18 plus 21 over 4 plus 9, all times this vector 2, negative 3, plus. So I'm going to multiply here, so I get 54 minus 28 over 36 plus 16 times this vector 6, 4. All right, so 18 plus 21, that gives me 39 over 13 times this vector 2, negative 3, plus 54 minus 28, that gives me 26 over 52, 6, 4. All right, so this gives me 39 divided by 13, that's 3, times this vector 2, negative 3, plus 26 over 52, that's the same thing as 1/2, 6, 4. Okay, so let's multiply these things in. So we do it down here. So I get 6, negative 9, plus, let's multiply this in because I can. So I get 3, 2. And if I add these vectors together, I get 9, negative 7. Oh my goodness, that's what Y is equal to, isn't it? So these were the two numbers, right, the C1 and the C2, that I could break up my vector Y to be a linear combination of these two vectors.